Hey guys, good morning. It is time for me to share one last little bit of information about circuits and chapter 15. So I wanted to go ahead and do that. There's a couple things I just wanted to walk through, a little bit of lecture on in terms of understanding effective resistance, and especially in terms of talking about effective resistance in series circuits versus parallel circuits. So I am going to pull up a document. I know, surprising. And we're going to talk about that for just a little bit. Okay, here we go. Oh, nope. Wait, get there. Okay. So I want to look at this document with you. We're not going to go through all of my notes. These are my class notes, but I did want to share a couple of things with you and look at the difference just in what's happening in a series circuit versus what's happening in a parallel circuit and why the math works out the way it does. So let's go ahead and talk about that. Here I've got a series circuit drawn, right? I've got three resistors, R1, R2, and R3. Now, what I want you, and let's take a minute and contrast that with a parallel circuit, right? Here's a parallel circuit where I've got resistor 1 and resistor 2. Now, the thing that's really important to understand about this is when you're trying to look at the math side of it and why the math works out the way it does, the thing you have to understand is, or have to look at is, what changes in a series or parallel circuit and what stays the same. And by looking at those things, it helps you discern, or at least it helps give some context for why the math is the way it is. So let's look at this down here. Let's look at this series resistor. Okay, so I've got three resistors, 1, 2, and 3. Now here's the thing that's interesting about a series circuit. So we know that the electric potential, V, equals the current times the resistor. So in a series circuit, the electric potential, across this resistor is going to be different than the electric potential across this resistor, which is different than the electric potential across this resistor. Why? Because the electric potential equals the current times R, and the resistors are not necessarily the same. So the electric potential across each one of those is different. What we do know is that the total electric potential is the sum of the electric potential across each one of these. So I can take my total electric potential and it will equal the electric potential across this resistor plus the electric potential across this resistor plus the electric potential across this resistor. Now, one of the things we also know about, so given that, let's go ahead and plug in or kind of flesh out this formula a little bit, right? So if V total then would equal I total times R total, right? And that would equal I1 times R1, my current across the first potential difference, times the resistor, the current across the second times the resistor, and the current across the third times the third resistor. Now, what's interesting about this path is that what is the current? The current is simply the charged particles, correct? That are flowing across for us in a given amount of time, right? So the current across this one has to be the current that's the same across this one, which has to be the current that's the same across this resistor. There's nowhere else for the current to go, right? So if it's flowing across all three of these resistors, then ultimately the current that starts out here will end up here. So what we know is that I total right here would equal I1, which equals I2, which equals I3. So I'm just going to call it I. The current across all of those resistors does not change. So that means what I can do when I go back to this formula here, right? I can say I times the resistance total equals I times R1 plus I times R2 plus I times R3. We can simply then factor out the I on both sides, and that leaves us with this equation. The total resistance equals simply the sum of the resistors. So in a series circuit, what we call an effective resistance, which is kind of the resistance of the whole circuit, is simply the resistance of all three resistors added together. So in series, determining your effective resistance is quite easy. You're just going to add up all the resistors. We would call that our effective resistance. Now let's take a look at a parallel circuit, okay? So again, here's a parallel circuit. I've got three resistors. Now what you can see is that there literally are three paths that the current can take. It's all going to start here, but it can break off across this resistor, or across this resistor, or across this resistor. So the current that flows through each one of these is literally different. If you can kind of think about it like you have 10 cars, right, heading to a certain destination. And the reality is all 10 of those cars that leave in one destination are ultimately going to end up at the final destination, but there literally can be varied paths through which they can get there. Okay, so the current that flows, the number of cars that flow through any one of the particular paths is not going to be the same. So back in our series circuit, the current that flows across each resistor is actually the same because it's the same number of particles. They have no other path of which to go. But in a parallel circuit, there literally are different paths through which the current can flow. So the current across each resistor is not the same. Is there anything that is the same? Yes. What we know in a parallel circuit is that, okay, so I'll get to that in a second. The other thing we do know, though, is that if I started, like going back to my car example, if I started with 10 cars and they all end up at the same place, then I'm going to end up with 10 cars. So the paths through which they flow may be different, but the total current at the end which simply is equal to each individual current added up. Because if I start here with a certain number of charged particles and they all end up over here, I know that the total of them is simply going to be how many flow through this path, plus how many flow through that path, plus how many flow through that path. So in this situation, our total current will equal the current of the three paths. Okay? So we can solve. So if that's the current of the three paths, we can solve each one of those using Ohm's law, right? V equals IR, therefore the current I equals V divided by R. So we can look at the potential difference. So I1 is going to equal the current across the first path will equal the electric potential across the first path divided by the resistance. I2 will equal the electric potential across the second path divided by the resistance. I3 will equal the electric potential divided by the resistance of the third path. Now, here is the question. What do we know about the electric potential? The electric potential across the circuit does not change. Okay, so in our series circuit, it was the current that stays the same across each resistor. In our parallel circuit, it's the electric potential that stays the same across each resistor. So we can say I1 equals V over R1, I2 equals V over R2, and I3 equals V over R3. So what can we factor out of that one? Well, for this one, we can factor out the V, and we end up with the current total equals the electric potential, which is the same across all three of them, multiplied by 1 over R1 plus 1 over R2 plus 1 over R3. So then we can say 1 over the effective resistance is 1 over R1 plus R2 plus R3 plus however many resistors we have in that parallel circuit. So that's 1 over the effective resistance. So obviously if I want to find the effective resistance, I'm simply going to find the reciprocal of my the reciprocal of 1 over of the effective resistance. Okay, so if I take the effective resistance, take 1 over that, that is going to give me my overall resistance. Whew. So I equals V over the effective resistance. Now I want to look at an example just real quick and explain that or walk through one. Okay, so here's the circuit. I've got a 12-volt electric potential. I've got 3 resistors. One is a 9.0 ohms, the other was 15 ohms, the other was 8.0 ohms. And I've been told that my I've been told my effective resistance. Oh, been told the current is 3.6 amps. Okay, so then what am I going to do? Okay, well, I'm going to look at each one of these. So I1 is going to equal the electric potential, 12 volts divided by 9 ohms. That's 1.3 amps. I2 is the second current is 12 volts divided by the 15 ohms, which is 0.80 amps. And I3 equals 12 volts divided by the 8.0 ohms. That's 1.5 amps. So now that's the current flowing through each path. So we have to, and we were told by the book that the total current was 3.6. So when we add up all the current that's flowing, what do we get? We get 1.3 plus 0.8 plus 1.5. Perfect, 3.6 amps. That was looking at the current. I was hoping to look at the, okay, so that's just looking at the current, and you can see how they all add up. I was hoping that we had one that was going to talk about an actual problem. Okay, let me pull up one from our homework that has an actual problem, and we'll look at that. So let me stop this screen share and pull up another screen share, and we will look at, just one sec here, let me pull it up. All righty. Okay, so here are some of the practice problems. I'm not going to go through all of them. The circuit, the series, it's very straightforward. Let's look at one. Here we go. I just determine the, I'm actually not going to find the whole thing. It's actually asking for the power, but what I'm going to go through is just the part of finding the effective resistance of this circuit. So I've got 120 volts and I've got 3 resistors. So again, 1 over the effective resistance is 1 over 9.0 ohms plus 1 over 19.0 ohms plus 1 over 15.0 ohms. Now, here again, the part of this is a little bit tricky, is 1 over 9 is actually, let me look at this. It's actually 0.11111 repeating. Okay, 9.0 has 2 significant figures, so I've got to report 0.11. 1 over 19 is 0. I have 526 is 0.5263157, right? This goes on. It's 0.5263. I've got 3 significant figures, so I've got to report 0.526. And then the 1 divided by 15 is 0.0666666 repeating. So again, I've got 3 significant figures, so what I'm going to report is 0.0667. Again, remember, these first 2 zeros are not significant figures. So what I end up is 0.11 plus 0.526 plus 0.0667. And when I add those, I actually get 0.7027. Oops, nope, that's, yeah, that's right, actually. Yeah, 0.7027. That is, hang on, 0.11 plus 0.526. Oh, it's 0.0526. I got a mistake there. And I get, okay, this is correct, 0.22931 over ohms. There should be a 0 in here. Whoop, 0.0526. So I get 0.22931 over ohms. What is my precision to? This one is to, actually it would be 10 thousandths. This one is to 10 thousandths. This one is to hundredths. So all I can report is 2 hundredths. So instead of reporting 0.2293, I'm going to say that my 1 over my effective resistance is 0.23. To take the reciprocal of that, right? 1 divided by 0.23 is going to be 4.3478. I have, again, 2 significant figures, so I would report an effective resistance of 4.3 ohms. And then what I do, I'm going to do it on here real quick. When I'm drawing these effective resistances, what I would do if this was me, I would redraw this like this. And I would say this is 120 volts. You have to excuse my trackpad. And this is going to be 4. Oops, that's not very good. Let's make it, try and make it look like a 4. 4.3 ohms. Okay. So that is how you simplify a series, simplify resistors that are in parallel. That's the process by which you do. The significant figures are a little tricky because it's adding and dividing, but that's how you're going to work those out. So hopefully that is helpful for you. I'm going to go ahead and end my screen share here now, and I will look forward to seeing you all on Tuesday. Have a great weekend.